was the first one. Yep, go ahead.
Okay. Hello, everybody. I'm Mohammed Sarbas, second year PhD student under supervision of Professor Waysan, and my research interest is designing optimal control through Mimax DDP. Today, I'm hosting this presentation. First of all, I want to introduce the GSC graduate student community. Welcome to the Spring 2024 seminar series. Today is February 7th, 2024, and Professor Waysan is the presenter. First of all, I want to introduce the GSC leadership team for the academic year 23-24. Roshan and Rachel are co-chairs, and publicity are Andrew and Avinash, and we have a big support team, as you see, and our mentor, that is Professor Farrokh Mistry. Our meeting regularly is on Wednesday at 7:30 p.m. and the meeting will be held by Zoom. If you want to join our meeting and having an invitation, you can send email to Rachel and Roshan through these two email address. And the time is set as per schedule of attending students. You can become the GSC member by scanning this QR code. I'm waiting some seconds on this QR code or going through this website. Also, we have the LinkedIn and the Facebook account that you can go there. I mean, by scanning these two QR codes or searching the GSC on these two platforms, you can go and get the latest news and have some posts that are on these two platforms. Besides, we have the GSC YouTube channel. If you miss all the recorded videos of sessions will be posted and uploaded on this channel. And if you miss any session, you can go there and watch those videos. There is a conference room in the engineering lab, Dave and Seisenberg team conference room, that you can go there and use some amenities like a couch, a whiteboard, cafe, a refrigerator, or also you can have some meetings there and take a rest there. If you want to have access, you can send email and get the access to that conference room in the engineering lab. Please sign via Google form that is sent in the chat, and by that link you can sign via the Google form link. And today, as I said, I'm hosting the presentation from the Professor Waysan, the assistant professor of School of Aerospace and Mechanical Engineering, and the title of presentation is Differential Games Under Uncertainties. Thank you very much.
All right, should I share my screen now?
I stop sharing, yes.
All right, so yeah, let's get started. Thank you all for coming, and if you have any questions, feel free to interrupt. So my topic today is on differential games under uncertainties, as I will mainly talk about the control side of differential games. So to start, I will give a brief review of general differential games. So differential games involve multi-person decision-making under conflicts in the context of dynamical systems. And the study of differential game was first originated with military pursuit games, such as dogfights between two aircrafts or missile guidance towards maneuvering targets. And those problems were studied by Isaac in his famous differential game book, published in 1965. And since then, differential games has been applied in a broad range of applications such as biology, economics, engineering, management science, operations research, etc. For example, differential games has been studied in biology to explain the process of evolution, and it also has been picked up in finance to study stock markets. And also one example of its application in engineering is in power grid systems or smart grids. All right, so in realistic scenarios, the decisions made by the differential game problems are susceptible to uncertainties. And here I summarize three typical types of uncertainties that can contribute to a dynamical system or to a differential game. So the first type of uncertainty is called environmental uncertainty. These are basically the exterior uncertainties that affect the dynamical system, such as if you have a bunch of ships in the sea, then they are affected by sea currents, or if you have a group of aircraft flying in the air, they are affected by they're affected by wind currents. And the second type of uncertainty is called dynamical uncertainties. And they normally come from the modeling of the system. So when we model the system, normally we can only have approximate model of the system, such as aircraft, manipulators, network system, biological systems. So when we write down the model of the system, they are only approximate model, and there's some dynamical uncertainty that come from these models. And another type of uncertainties is called observation uncertainties, and they generally come from different observers we place on our system so that we can get the observations from system. And those observations are subject to uncertainties or noise or disturbance. So when we apply the control on those type of systems, we have to deal with uncertainties. All right, so to deal with this type of differential game problem under uncertainties, we're trying to utilize this so-called game-theoretic differential dynamic programming technique. So I will talk about this game-theoretic differential dynamic programming, and then talking about this game-theoretic DP subject to control constraints, and then extend it to stochastic systems, and then talk a little bit about some applications to system with dynamic uncertainties. And I will draw my conclusion with my current research. All right, so the game theoretic version of differential dynamic programming is actually an extension of the original differential dynamic programming technique, which apply to optimal control problem. So for optimal control problem, the goal is that we have a control that tries to minimize or maximize some objectives while trying to drive the system states from some minimal state to some desired state. So this differential dynamic programming is basically an algorithm that finds the optimal trajectory along with optimal control with some iterative methods where you can start from some nominal control and state pair, control and state trajectory pair, and through these iterations, eventually obtain the optimal control and optimal trajectory. So original differential dynamic programming, or DDP, was studied by May and Jacobson in their book, published in 1970. And over the years, differential games has been extended to different areas. For example, it has been studied with the state and control constraints. and extension to min-max problem, where one control tries to minimize the cost or minimize the performance measure, and the other control tries to maximize it. And they also have been applied to receding horizon DDP. Basically, in realistic scenarios, if you want to apply a control, you want to apply this control in this receding horizon fashion so that you can actually get a control that affects the current state of the system. And it has also been studied for stochastic systems subject to optimal control problems, such as iterative linear quadratic Gaussian algorithm and the stochastic DDP algorithm. And DDP also has been combined with machine learning methods to study to apply DDP on the learned dynamics, such as again iterative LQJ with learned dynamics, and the probabilistic DDP, where the differential dynamic programming is applied to a system learned through Gaussian process. All right, and here is the general problem formulation of this game theoretic version of differential dynamic programming. So it basically applies to a system subject to a dynamics and a cost, and the value function is the min-max of this value of this cost. And you can see that in this dynamics, we have U and V, which stand for two controllers. Here, this control U is trying to minimize this cost, and this control V is trying to maximize this cost. And this cost has two parts. One is the terminal cost, which is the cost that appears at the terminal time, and the other is called the running cost, which is accumulated during the process of the system. So this is actually a standard dynamical system problem formulation. The only difference from this and optimal control problem is that instead of one control in optimal control problem, now we have two conflicting controls. One control is still trying to minimize the cost, which is you can consider it as a control in optimal control problem. But then we include another control that tries to maximize this cost or trying to sabotage our goal. So control U, you can think of it as a stabilizing control, which tries to stabilize the system or tries to drive the system to their desired goal state. Whereas this V is called the destabilizing controller, or the control that tries to drive the system away from the desired state. So here, this U and V basically are competing controllers. And again, the scenarios where this can be applied, like the pursuit event problem we just mentioned, where this control U tries to catch another aircraft, and control V is the control of the other aircraft that tries to avoid the contact. And another application of this differential game setup is that you can again think of this U as a control which you apply to a system, and think this V as like the worst case scenario. Like if you have a disturbance, and this V can be considered as the intelligent disturbance that can act on this system. So basically, if your control can drive your system to the desired goal, even subject to this worst case, this intelligent controller, then this control would be able to drive your system towards the desired goal states subject to some random noise, random disturbance. So that's another application of this differential game setup. All right, so for this this game theoretic differential dynamic programming algorithm, the way we try to approach it is that we try to do local approximation of the dynamics and the value function around the nominal trajectory, so that we basically make it linearize the dynamics and expand the value function through the Taylor series expansion up to second order. And through this, we can get an approximation of the value function and the dynamics about a nominal state and control trajectory. And then through the iterations, we'll try to drive this trajectory towards the optimal trajectories. And the output of this game theory DDP algorithm are the optimal trajectory, optimal state and control trajectories, and also the gains of the control, so that this control can actually be applied to in a feedback scenario. So if you talk about optimal control problem, if you're familiar with optimal control problem, normally you get a control which is open loop control. So that control can only apply to a specific state trajectory. But if you have feedback control, then that control can be applied to many scenarios. So even if your state is subject to disturbance, you can still apply this feedback control so that you can guarantee that the control or will drive your state towards the desired state at least. All right. So here is the basic idea of this game theoretic DDP algorithm. So we start with some nominal state trajectory. So suppose we just gave some nominal control and we apply this control to our dynamics, run this dynamics towards the final time, and we generate this state trajectory. Notice here that if we pick a nominal control or pick a random control, then we cannot guarantee that this control will drive our state trajectory toward the desired goal. But what we can have around this nominal trajectory is the linear approximation of dynamics and the quadratic approximation of cost function. And then once we have that information, we can try to backpropagate this quadratic approximation of this value function V, which this value function basically encodes the optimal control you should choose. And we can find optimal corrections in both control U and control V so that we can actually update this control. So here this LU is the feeds forward part of our control updates, and the capital LU is the feedback part of our control update. And those two terms are functions of this value function and its first and the second order approximations. So once we get this optimal control updates, we can basically get a new control where U is equal to previous control plus delta U and V is previous control plus delta V. So that with the new control, we can generate a new trajectory. And that trajectory will be better than our current trajectory because we pick here optimal control updates. So like I said, this is the iterative algorithm so that through the iterations, this updated trajectory will go towards the goal step by step, and eventually we'll be able to get optimal state trajectory along with the optimal control. And here, this LU and capital LU, LV and capital LV will be our gains. Especially this capital LU and capital LV, they will be our feedback gains so that we can use those feedback gains to generate a feedback control to apply to a system with stochastic disturbance or like a Gaussian disturbance. All right, so here is a brief summary of the game theoretic DDP algorithm. So for this algorithm to work, you need the initial condition of the dynamics, initial minimizing and the maximizing control. These are basically some nominal or some random control pair you pick. And you need the final time, some multiplier, and the large integer n for the iteration to proceed. And again, the output of this algorithm are the optimal control trajectory pair U star and V star, and optimal state trajectory along with the corresponding optimal gains. So here is how the algorithm works. So within this iteration, you first generate the trajectory from initial condition of the state and the nominal states, nominal control U and V. And then you compute the value of this value function, first order and second order approximation at TF. And then you integrate the value function backwards in time and integrate the delta x, which is the linearized state equation forward in time. And once you get once you integrate those two values, you will be able to calculate your feed forward and feedback gains. And through that, you can compute this optimal update on the control U and V, and can update this control here. We introduce this multiplier gamma because it's a standard approach in computer science where you basically reduce your times, reduce the change in your control so that you don't do some sudden control so that the states will become like the trajectory will generally approach your goal trajectory. All right, and then you can set the new control U and the new control V as nominal control and repeat this approach. And eventually this algorithm will convert to the optimal trajectory, and you will be able to get optimal controls. All right, so here are some examples where we apply our algorithm is. So the first, we apply our algorithm to an inverted pendulum problem under disturbance. So the idea we did this is that here this W is a disturbance. So first of all, we replace this W with an intelligent control V. And then we apply our game-theoretic differential dynamic programming approach on this differential gain problem between control U and control V. And then we apply this control U in its feedback form on this original problem under disturbance W. So here are some results we have. So you can see these are the trajectory of this theta angle of the inverted pendulum and the theta dot, which is the angular velocity of this inverted pendulum. And here we want to drive this theta from pi to 0, so that we want to invert the pendulum, and we want theta dot to be 0 at the final time. So here are some trajectories under different choices of our V. So here our V is this relate to the cost with respect to the intelligent disturbance V. So by changing this value of our V, what we're essentially doing is that we're telling the V, we're changing the intensity of our intelligent controller, intelligent disturbance. So if our V is large, it means that we don't assume this disturbance to be too severe. Whereas if our V is small, then what we assume is that this RV is this V is very strong, so that this controller U is competing with a strong controller V. So basically, we have more control authority on the V, and you can see that from this result here, we run this inverted pendulum under disturbance for 100 run-outs, and we draw the standard, we draw the mean trajectory and the standard variance of this 100 trajectories here. And you can see that as our V decreases, it means that we assume more intensity on the disturbance. The behavior of this optimal trajectory also changes. And here you can see that if we assume a more intense intelligent disturbance, then our control actually tries to drive this system towards the desired states earlier, so that it can guarantee that, because if you're closer to the desired states, you have more room to control. So you want to drive the system towards the desired states earlier if you are subject to a stronger disturbance. Whereas if you are subject to a more like a disturbance that is not that intense, then you have more room to wiggle with, so you actually can drive the system towards the goal states in a later. So you can see that this trajectory goes to 1. This trajectory goes to 0 later than this trajectory, subject to more intense intelligent disturbance. And similar can be seen on this. And you can also see from the theta dot figure that if you are subject to more intense disturbance, your standard variation or your standard variation will be larger. So you can see that this value is much larger compared to less intense intelligent disturbance. And here, again, here we are applying this controller U subject to this Gaussian noise, Gaussian white noise. So that's why we have 100 trajectories that look different. So we need to get the mean and the variance of these trajectories. All right. So back. So the next thing we apply this algorithm, this game-theoretic differential dynamic programming algorithm, onto a quadcopter with conflicting controls. So here, this quadcopter has 16 states. It has positions, Euler angles, velocities, and angular velocities. And this omega are the velocities of the spinning velocity of each propeller. So quadcopter or quadrotor has 4 propellers. So this omega has dimension 4 here. And we have here the cost on this conflicting control U and V. And we are trying to drive this quadcopter from the original state to the desired state. So somehow this will not play in this Adobe Reader. So let me try to share this video here. So here, this is the initial state of the quadcopter, and this is the desired state of the quadcopter. And here, this quadcopter is subject to 2 controls. One is the control U that will try to drive the system towards the desired state. Another is the intelligent disturbance controller V that tries to get away from this desired state to minimize the cost. And you can see that despite this intelligent controller, wait, let me see. Despite this intelligent disturbance, we could still drive it. Okay, so here we go. So it starts at this position, this orientation, and here is optimal trajectory it generates, and subject to the optimum control U and V, and it was able to go to its desired state and orientation, position and orientation. All right, so going back to the presentation. So here we apply this game-theoretic DP algorithm to the system with 16 degree of freedom, and we were still able to run this algorithm. And the next thing we'll talk about is control constraints game-theoretic DP. So why do we care about control constraints? That's because most of the mechanical system we're dealing with nowadays have different types of control constraints. So for example, if we have a car, it has a turning radius constraint, and it also has a speed constraint. And for example, for aircraft, it has the different type of control surface constraint. It's aileron flap angle, the flapper angle, the rudder angle, and the thrust. So different type of control constraints on aircraft, and there are even more control constraints on a humanoid robot. So that's why we have to consider control constraints when we are dealing with realistic systems. So here is how we can apply the constraints to a game theoretic or combine control constraints with the game theoretic differential dynamic programming algorithm. So the type of control constraints we consider here are only Boch's constraints. So basically, we assume here that our control constraints are subject to a maximum value and a minimum value. And all the other problem formulation are the same with original game theoretic DP algorithm. And here, this is how we deal with the control constraints within each iteration of game theoretic DDP algorithm. So the idea is that we want our updates. Once we update our controller, we want the updated control to be within this bound as well, so that we'll know that at the end of the iteration, we'll be able to generate the control subject to the control constraints. And the way we approach this problem is that we generate two quadratic programming problems, one on delta U star and one on delta V star. So the basic idea is that we want our delta U star to be both optimal and subject to control constraints. And similarly, we want this controller V to be both optimal and subject to the control constraints on V. But one of the problem of this differential gain problem is that those U and V has to be chosen at the same time, so that this optimal U is not fixed until we fix optimal V, and vice versa, optimal V is not fixed until we pick optimal U. So the way we deal with this problem is, again, we use some iteration methods to try to approach our optimal delta U and delta V. So the way we do it is through this control update algorithm. So the idea is that we first fix our delta V and solve the quadratic programming on delta U. And once we solve, after we solve the quadratic programming on delta U, we use that delta U, fixed delta U, to solve the second quadratic programming problem and find the updated delta V. And then we use this updated delta V to find updated delta U again, and we do this iteration until we find optimal delta U and delta V eventually. All right. So this is also like a standard method to deal with a problem where you have to pick two optimal solutions at the same time. So instead of trying to find them at the same time, you try to find them iteratively through iterations. All right, so here are some simulation results for problems subject to constraints. And this is again the quadcopter problem. So here we ignore the change or the dynamics on the propellers, or we ignore the change on the motors of the quadcopter, only consider the quadcopter itself. So here we have the states includes the position, or the angle, the velocity, and the angular velocities. And this is again subject to two controls, but this time we assume only a control constraint on U, because for this problem, basically we assume this V to be an intelligent disturbance, So we don't give it any control constraint on V. We only impose control constraint on U, which is needed because control U is basically what we need to control this quadcopter. So you can see that subject to these constraints, we were able to find this optimal control trajectory so that it's tracking this figure 8 trajectory. And so we actually did this simulation in the gazebo environment. And so we were able to kind of track this trajectory, and these trajectory are all generated by DDP algorithms. And you see that it was able to track this figure 8, impose the figure 8 trajectory. And also satisfy the control constraints. All right, and the next thing we did is that we did an experiment on a 2-player pursuit event game problem. So once we have this 2-player pursuit event problem where one quadcopter is trying to chase another quadcopter, then this control U becomes the control of the pursuer, and this control V becomes the control of the evader quadcopter. So that this time, both of those controls are constraints, and we were able to find the control constraint, optimum control from this control constraint game-theoretic DP algorithm. And we have the simulation trajectory on the left, and the trajectory recording of the real drones on the middle, and the snapshot of those two quadcopters flying midair. All right, so the next topic I'm going to talk about is this stochastic version of game-theoretic DP. And again, the reason we want to deal with stochastic system instead of deterministic system is that the stochastic system actually play a fundamental role, and the stochastic process play a fundamental role in models of phenomena in many fields, including science, finance, engineering, etc. And here for engineering applications, some area that the stochastic system need to be taken into consideration involve network systems, or another example is where you assume that you get your states from the observations. And if you get your states from observations, then that state information is subject to some noise, some disturbance. And you can model that disturbance by modeling the dynamics with the stochastic dynamics. So that's another way this stochastic dynamics can be taken into consideration. So sometimes, even if you're dealing with a mechanical system, sometimes people model that mechanical system with the stochastic dynamics. So some typical stochastic system involve, on the left is Brownian motion. I don't know how many of you are familiar with it. It's basically a phenomenon where if you consider a system in the molecular level, so basically if you have a large particle, an example is if you have a large particle, you drop a particle in the water, and those particles will do a random walk or do a Brownian motion in the water. And the reason is because that particle is interacting with the water molecules. So here is a typical experiment of particle motion affected by the random collision with smaller particles. So that's called the Brownian motion or random walk, and you can approximate that with a stochastic model. And another area where stochastic system is considered is the stock markets or the financial system. So in those type of systems, because there are so many players involved in the system, eventually the system behave almost like a random system or stochastic system. So you can use stochastic dynamics to approximate that. And another system, like we mentioned in engineering applications, is the smart grids. So again, you have many users that contribute to this smart grid so that you can approximate it with the stochastic system. And you can try to find control on this stochastic system. All right, so here is the problem formulation for stochastic game theoretic dynamic programming or stochastic differential game problem. So it involves dynamics. Now we have our dynamic is subject to some noise, some stochastic disturbance, and this disturbance is modeled by some normal distribution or Gaussian noise. And our total cost, instead of a deterministic cost before, is now expectation of a random cost. So basically a mean of a lot of run out of random cost. And our value function will stay the same or very similar to deterministic case. This value function is trying to say that our control U is still trying to minimize this cost, where our control V is still trying to maximize this cost, subject to this stochastic dynamics and the expectation cost. And the way we approach this problem is again very similar to deterministic case, where we do a first order expansion on the dynamics and the second order expansion on the value function. So let's forget about this math. So basically what we did is that when you expand the states and value function up to second order in stochastic space, then you have some extra terms popping up due to this stochastic process. So eventually you have to consider more terms, but the idea is still the same. So you are still starting with some nominal control and state pair, and this state is the expected state or mean of the state. And this control and state pair will be updated by finding the optimal update on delta U and delta V. And eventually through the iterations, we find the optimal mean of the state trajectory and optimal control U and V. All right, so here we apply this system to a card pole under disturbances. And again, we have, so this time we have two controls and our disturbance appear in the dynamics of the system modeled by this Gaussian noise or this normal distribution. And our goal is to invert this pendulum on this card. And so we have to, our controller has to drive this angle theta to 0 in the end. So here we impose the constraint, the terminal constraint on x dot, which is the speed of the card, and on the angle theta of this inverted pendulum, and the theta dot, which is angular velocity. So we want this control to be able to invert this pendulum at terminal time 3 seconds, where we want 0 velocity of this card and the 0 velocity of this mass or this pendulum, and we want to invert this pendulum by driving the theta from pi to 0. And you can see that subject to this disturbance, we were still able to drive at least the mean of this state trajectory toward this goal state. Here we did not constrain on the position of these cards because that's not relevant. We can still do it, but we don't have to. do it. So we only constrain on the speed of the charge, the final angle of the pendulum, and the angular velocity of the pendulum. So you can see that after we do the run out for 100 trajectories and calculate the mean and the standard deviation of these trajectories, you can see that the mean trajectory was able to go to its desired states, and this red line denotes the desired states. All right, so the next topic I'm going to talk about is how we can apply this game theory differential dynamic programming to system with dynamical uncertainties, and in particular where we have approximate models of the system. So again, as we mentioned in the very beginning, most of the systems we are dealing with are only approximate models. So what we can actually do is to apply machine learning algorithm to learn the error model between the nominal model and the real model of the system. And then we can set up a nonlinear H infinity control problem. Here, what this H infinity control does is that it can actually drive a system. It synthesizes the control that drives the system to the desired states under disturbance. We'll talk more about it later in the later slide. And then we utilize the game theoretic DDP algorithm to solve that problem to find the H infinity control. So here is the problem setup. So here, assume that we have a deterministic dynamics. Of course, we can extend it to stochastic dynamics, but let's first consider deterministic dynamics system. So here we have, we assume that our dynamics is subject to a nominal dynamics and the difference between the nominal dynamics and the real dynamics. So here, this nominal system model is given to us. For example, if you have an aircraft, we know the approximate model of the aircraft. That will be our nominal system model. So our goal is to try to learn this unknown aerodynamics through the data and the Gaussian and some machine learning algorithm. So what we did in this study is that we modeled aerodynamics through the Gaussian process. All right, so once we model this aerodynamics, we are able to get a better model of the system. And then we can apply our control on this model, and we'll get a better model. We'll get a better control to control our real system. So for this machine learning methods to approximate the aerodynamics, we utilize this Gaussian process. A Gaussian process is a stochastic process such that every finite collection of its random variable have a joint Gaussian distribution. And the Gaussian process has been utilized to approximate dynamics in previous literatures. And this Gaussian process has a so-called Gaussian kernel. And what it does is that it takes in the data, observation data, like the state information, the delta F information obtained by F minus F bar. And if then we are given a test input, then we can write down the joint probability distribution. And for the Gaussian process, we assume this joint distribution to be still Gaussian, so that from this joint probability distribution, we'll be able to synthesize this F of H star, which is a dynamic delta F of H star, which is the aerodynamics subject to this new input. So once we have that information, then we can basically get a better model of the system and apply control on that system. All right, so the next thing we did is that we try to find the control on the new system, which is modeled by H dot used to F bar plus delta F. So we utilize this so-called H infinity control which tends to synthesize controllers to achieve stabilization with guaranteed performance. So this, technically speaking, this H infinity control is subject to some H infinity norm, and it's trying to optimize. The control is again trying to optimize some performance measure subject to this H infinity norm. And it has some guarantee on the performance subject to disturbance. So from this Bassar's book, H infinity optimal control and rate min-max design problem, dynamic game approach, it tells us that the H infinity control problem can actually be recast as a zero-sum differential game problem. And this zero-sum differential game problem is what we studied in game theoretic differential dynamic programming. So that's what can be solved by different game theoretic DDP. So basically, what from Bassar's book we can consider, if we consider soft constraints, if we are given a nonlinear H infinity control problem, we can come up with a soft constraint differential game problem associated with that problem. And then if we find the control of this differential game problem, we'll be able to get the H infinity control eventually. All right. Sorry about going backwards. All right. So now the differential game problem associated with the H infinity control problem is given as follows. So here we have H dot equals to F bar, which is a nominal dynamics, plus mu of X. Here, this mu of X is the mean. This mu of X is the mean of this delta F. So that's basically the Gaussian process approximation of this aerodynamics. So we add this mu here as well. But in order to incorporate the disturbance as well, we add another term. So this term will mimic the disturbance that contribute from this delta F. So this term is this W times C times V. And V is again some intelligent disturbance. And the W here encodes the standard deviation information of disturbance. And this information comes from this Gaussian process. So for a Gaussian process, it not only learns the mean of this delta F, it also learns the variance of this delta F. So this variance information can be incorporated into this this disturbance. This time you can think of it as the intensity of this disturbance. So if the variance of Gaussian process is large, it means that it didn't learn a very good model. So that's F bar plus mu is not very good. So that's why we have to add this actual term where W reflects that term sigma, so that with the larger sigma, we have a larger W. So that's we basically assume that we have a more intense disturbance so that we can find a more conservative control to drive our state to the desired states. And C here encodes the information of a structure of noise known a priori. So for example, if you know that your noise or your disturbance only from the control channel, then you can design your C accordingly so that your control only contributes to the control channel instead of the full states channel. All right, and then we also come up with a new cost function or performance measure subject to this differential gain problem where we have one actual term on V so that the optimum controller can ensure disturbance attenuation bounds gamma. All right, once we come up with this differential gain problem subject to this cost, then we can basically use game theoretic DDP to solve it. So that's what we did, and once we solve this control feedback control U, then we apply this control U to the original system. So then we apply this control to this to the original system subject to disturbance, and here are some results. Again, we apply this system. We apply this algorithm to a quadcopter system, and here are the results we have. So here we only plot the mean of the state trajectory in 100 iterations, and the corresponding goal states are drawn in dashed right. So eventually, at the terminal time, we want our state to go to this dashed red value, except for those last four states. Last four states are the spin speeds of the propellers, which we don't enforce any constraint on it. So here, our states 1 through 12, the first three states are the position states, and H4 through H6 are the Euler angles, H7 through 9 are the velocities, 10 through 12 are the angular velocities. So basically, what this plot is telling us is that we want the quadcopter to go from the initial position, which is 0, 0, 0, to the final position, which is 3, 5, and 1. And so we want a change in the yaw angle here at 6, and we want the terminal Euler angles to be 0, 0, 2 pi, so that we want a change in the yaw angle, but we want the pitch and roll angle to be 0 at the end. And also we want the velocities to be 0 and angular velocity to be 0 in the end. You can see that we were able to achieve this desired state at the end of our time, which is 5 seconds. All right. So the last part of the topic, I will probably go through this fast, is what happens if we only know the structure of the system, but we don't know the dynamics of the system. So then we can use some machine learning method to learn the full states, full dynamics of system. So for this type of problem, we assume that our dynamics is x dot equals to f of state plus j of state times the control u plus j2 of state times control v. And we assume that this f, j1, j2, which are state dependent, are unknown. And our total cost is a quadratic cost on the states and the two control u and v. And for this type of system, we were able to learn this unknown dynamics from data and through a neural network approach. And this adaptive dynamic program, what it does is that it approximates the value function in the Hamilton-Jacobi-Bellman equation associated with optimal control problems. And so we have machine learning methods, we have machine learning algorithm to approximate the dynamics as well as the value function. And we were able to generate the optimal controls and optimal trajectories in the end. So here we use a recurrent neural network to approximate the dynamics. Let's ignore those actual terms. And we prove that our recurrent neural network is able to approximate the original states, original dynamics. And then we apply an online policy iteration algorithm to solve the Hamilton-Jacobi SX equation, which is subject to a differential gain problem. And here is the min-max adaptive dynamic programming algorithm. And we approximate value function with the neural network as well. And eventually we were able to both approximate the dynamic. This is a real dynamic trajectory. This is our approximate dynamics trajectory. and we can find the control subject to this trajectory as well. And here is how the weights propagate with time. And this is again for inverted pendulum with conflicting control problem. And we also apply this algorithm on a chaos system where we want to drive the state to zero, two states to zero. And you can see that we again was able to approximate the real system with our approximate state through neural network. And we were able to find optimal control through the so-called policy iteration algorithm. All right, so I want to end my talk with some of my current research. So currently my research focus is on perception, state estimation, planning, and control of a multi-agent system. So previously I was mainly focusing on the control part, but I'm also interested in the perception, state estimation, and planning parts. So I'm doing some different games with partial observability to take the state estimation into consideration. And I'm also trying to find some safe machine learning policies for perception control that combine perception with control. And I'm also trying to do some swarm navigation control, basically navigation control on a swarm of drones, a swarm of robots. And that's my current research focus. And again, this different game can be applied to all those problems. All right, that's the end of my talk. Any questions, comments?
Thank you very much, Dr. San. If anyone has any question, please ask.
I have a question, and then I'll start my video.
Mm-hmm.
I can't see me. Is it working?
Yes, yes.
Okay, hi. Okay, so I'm not a programmer. I'm not in your field at all. But this is interesting because I'm looking at how this could apply to social issues.
Mm-hmm.
And you mentioned economics, and I know some about that. How do you go about choosing? What are the factors that you use to choose which strategy to look at for identifying, you know, the components of the error model and
Exactly.
what do you choose between?
I'm not sure if I picked up your question clearly. Did you say like how do I pick the strategy of the controller? Or?
Yeah, like so you've presented several different strategies for finding the optimal solution, right? What are the pros and cons of each one, right? Like how would you go about deciding, like, if I wanted to take one of these and try to apply it to social issues, what should I consider?
Yeah, so I think if we want to apply to social problem, like so actually different game has been applied to network systems. And basically what we do is that the dynamics will be the same, but so sometimes when you have social network, it will be a multiplayer problem. So here, this is a two-player problem. This is like a two-player U and V. So for a social network, that could be multiple players. So that would be a multiplayer problem. So for a multiplayer problem, you basically formulate the problem as a multiplayer differential game problem. And then you can solve for that problem. Or another approach for that type of problem is people actually formulate as a so-called mean field game problem. So idea there is that if you have too many players, then you can think of all those players as one big group, so that you get a mean field dynamics from all the effects of individual players. So in end, you have only the mean field control and the mean field dynamics, and you can find the control of the mean field dynamics. So on that area, basically the idea is that instead of trying to control one player, you are controlling like the group of players together. So it's like a control of distribution rather than control of dynamics. So that's two ways to this can be applied to a social network problem.
Thanks very much. I appreciate that.
So, right, I guess there is no more questions.
So, thank you very much, Will. This was a very interesting talk. And as you've seen, it's garnered quite a lot of positive comments in the chat.
Mm-hmm. Well,
I
I
do
didn't
have-
follow the chat, but
Yeah,
sorry
but you
about
should take a
that.
look at it.
Mhm.
I do have a comment for you.
Sure.
See, in game theory, it is imperative that the best response correspondence is perfect. Okay? And what you just said, that you're going to aggregate people,
Mm-hmm.
that means that the best reply correspondence is not perfect. You'll get answers, but you're going to be violating the Karush-Kuhn-Tucker conditions.
Right.
So you can do it, but what it means is that you are violating the fundamental Karush-Kuhn-Tucker condition.
Mm-hmm.
And then how can you say that the results are right?
You cannot claim it's optimal anymore, but you can still guarantee that. So for example, for a mechanical system, right, you can still guarantee that the feedback control will drive you to the desired states. So it won't be this control it won't be the open loop control you find by solving this problem, because the open loop control has to assume this V is playing optimally, like you said, right? But if you apply a feedback control, that control can still drive your system toward the goal states. Although it's not optimal, but it's kind of a conservative controller that takes into consideration of this worst case scenario. So that's basically what we generate. That's what this feedback control is. And another thing we can apply this is this receding horizon approach, right? So if the state is deviating from the perfect state, which we assume, then we can do it through the receding horizon or MPC approach, where we can recalculate our control if we have enough calculation power.
So in essence, you're saying you will not get an optimal solution. I accept that. If you say it's a satisfying
it will not be optimal unless the other player is playing optimally, right? So yeah.
Great. Well, thank you very much. It's our practice to stop recording, and after that we continue the chit chat for those who would like to continue. There are very few people, but I'm going to stop recording.
Sure.
And then we